Okay, can you hear me? Okay, fine. Okay, let's begin. Today is a test for my astrophysics seminar, and we will give just a little test, a little class just for the first time. Okay, our reference is lecture. No, sorry. Yeah, is a textbook. And we will follow the order of the chapter from my plan is from chapter 1 to chapter 4, so we start from stars. Yeah, and today we will give just the first or the primary content of stars, hydrostatic equilibrium equation. Okay, so let's begin. Well, consider a star. With its nominal radius r, capital R. And suppose the star is in equilibrium and it is spherically symmetric, so the density and the pressure are only the functions of radius r. Yeah. So first let's use the equilibrium condition to infer some interesting facts. Consider a thin shell of the star with radius r and thick dr. Okay, so the mass of this thin shell is dm equals to 4 pi r squared times rho r dr. Okay, and the gravitational force the thin shell feels, Fg, is equals to minus capital G times 4 pi r squared rho r dr over r squared times mr equals to minus 4 pi capital G rho r mr dr. Well, let's explain this minus signal. This minus sign refers to the gravitational force points inward to the center of the star. Okay, and this function mr is just the total mass interior to the radial stars, which satisfies this important equation dmr dr equals to 4 pi r squared rho r, which can be easily verified. Okay, and we have an important initial condition, 0 equals to 0, and I think it's very understandable, so I won't explain it. Okay, so for equilibrium condition, we also need an outward buoyant force, which provided by the pressure of the stars. Now let's explore this. Consider this thin shell again. The thick is dr. So the buoyant force equals to the pressure equals to the pressure in the inner surface of the shell minus the pressure of the outer surface of the shell. So it equals to 4 pi r squared times pr divided minus pr as dr, and equals to minus 4 pi r squared p prime r dr. This prime expresses the derivative with respect to the radius r. And we use the equilibrium condition Fg as Fb equals to 0. hence we obtain the fundamental equation of a hydrostatic equilibrium for stars. dPr over dr equals to minus gmr rho r over r squared. This is an important equation which we will use later. Okay. So let's infer important inequality for pressure PR. We'll recall the two important equations. dmr over dr equals to 4 pi r squared rho r, and this one and the fundamental equation we have just obtained. Now we will use these two equations to infer the inequality for pressure. Consider this derivative. That's gm squared r divided by 8 pi times fourth power of r. And we obtain minus gmr rho r over r squared as g over 8 pi times 2 mr times 4 pi r squared rho r times fourth power of r minus 4 times third power of r times m squared r over the eighth power of r. And simplify the whole expression, we obtain minus gm squared over 2 pi times the fifth power of r. This value is obviously non-positive. So if we set a function fr equals to pr as gm squared over 8 pi times fourth power of r, we know that this whole derivative is non-negative, which means when r increase, the value of the function fr decrease. And we'll obtain fr f0 will larger than f capital R. Capital R means the nominal stellar radius. So let's use this relation to infer the inequality for pressure in the center of the stars, P0. So let's begin. Let's suppose that the density at the center of the star, rho 0, is finite, which means when r tends to 0, mr will proportional to the third power of r, which means this limit mr squared over fourth will tend to 0 when r tends to 0. And on the other hand, in the surface of the star, the pressure will be assumed to be 0, and the mr will equals to the total mass m0 of the star. And finally, we obtain the inequality for the central pressure of the star, P0, will larger than g m0 squared over 8 pi times fourth power of capital R. Okay. Next, we will talk about energy. Well, first, let's denote the gravitational potential energy by omega, capital Omega. Okay, according to the definition, minus omega will be defined as the energy we need to remove the mass of the star from its original place to infinity. Okay, that's the definition for the gravitational potential energy, and we can use this to obtain the expression for omega. First, let's consider the energy we need to remove the shell from its original place to infinity. The energy will be gmr times 4 pi r square rho r dr times integrate from r infinity dx over x square, and the result is 4 pi. Wait a minute. Okay, 4 pi g r mr rho r dr. Okay, this is the energy we need to remove the thin shell from its original place to infinity. Hence, minus omega equals to 4 pi g integrate from 0 to r m r rho r dr. Okay, and if we want to deal with this integral, well, we need to integrate it by part, and obviously we can use this fundamental equation for equilibrium, for hydrostatic equilibrium for stars, and we can substitute the gmr rho r over r square to the expression of minus omega, and we can obtain omega equals to 4 pi integrate from 0 to capital R, third power of R times dpr dr. Okay, then we can integrate by parts. This equal to 4 pi third power of R pr 0 to capital R minus integrate from 0 to capital R pr times 3 r square dr. Okay, notice that the first term will vanish at both endpoints, and we obtain 4 pi. No, wait, sorry. We obtain minus 3 integrate from 0 to r pr times 4 pi r square dr. This is the gravitational potential energy of the star. And on the other hand, we can use the gravitational potential to calculate this gravitational potential energy. Okay, we know the gravitational potential, phi r equals to, well, I think I should write it down. Yeah, well, potential energy, and phi r. This is the gravitational potential. It equals to minus g r integrate from r to infinity, mx dx over x squared. We use a different variable here because we want to distinguish it from the original variable r. It can also be r prime or other things. Okay, and we know that the minus derivative of the potential will be the gravitational force per mass minus g mr over r squared, just like the condition in electrodynamics. Well, it's just the same. Okay, and now we consider this expression, integral from 0 to infinity, phi r m prime r dr. Integrate this by parts. Is equals to phi r mr infinity minus 0 to infinity mr phi r dr. Okay, and notice that we notice the boundary condition when r tends to infinity. Obviously phi r tends to 0, and when r tends to 0, mr tends to 0. So the first term vanishes, and we obtain minus g 0 infinity m square r over r square dr. And we integrate this again. We integrate this by parts again, and we obtain minus g minus m square over r 0 to infinity minus integrate from 0 to infinity minus 1 over r times 2 mr times m r prime dr. Okay, now use the boundary condition again. When r tends to infinity, 1 over r tends to 0. When r tends to infinity, 1 over r tends to 0. And when r tends to 0, mr proportional to the third power of r. So mr square over r tends to 0. Finally, we obtain minus 0, integrate from 0 to infinity, 2 mr over r m prime dr. And use the expression for m prime r, we obtain minus 2 for pi g. Integrate from 0 to capital R, mr rho r times r dr. Compare this expression to the expression of omega, and we find that it's just 2 times omega. Finally, we obtain the gravitational potential energy for the star can be expressed as omega to 1/2 integrate from 0 to infinity phi r times m prime r dr equals to minus 3 times integrate from 0 to capital R pr times 4 pi r square dr. Okay. Besides the gravitational potential energy, a star also has thermal energy. Suppose the total thermal energy of stars is E0. We can express it as integral from 0 to capital R epsilon r times 4 pi r squared dr. And this epsilon r is just the density of internal thermal energy of the star. So the total energy, capital E. Well, we don't consider the relativistic energy now, so we won't include the rest energy of the star. The total energy just equals to the sum of the thermal energy and the gravitational potential energy. E0 as omega equals to integral from 0 to capital R epsilon r minus 3 pr times 4 pi r squared dr. Okay, so we can find in this expression that if epsilon r less than 3 pr, the total energy will be negative, and the star will be stable. This star mass will not be dispersed to infinity, so it will when the total energy is negative. Okay, so in some case, this epsilon will be proportional to pressure, and we call these stars polytropes. We will discuss polytropes in later seminars. It's an important class of the stars. Well, and in this case, we really denote this relation as epsilon equals to p over gamma minus 1. Okay, so together with the expression of E0 and omega, we can easily obtain the following expression. E0 equals to minus E over 3 gamma minus 4, and the gravitational potential omega equals to gamma minus 1 over gamma minus 4 over 3 times E. Now, for stable stars, we know the total energy will be negative, and of course the gravitational potential energy omega will be negative will be negative too. So we obtain the stable condition is gamma larger than 4 over 3. Okay. We'll use this will be useful in later discussion about stars. And today's test will be. I think today's test is I think it is appropriate to end today's test seminar now. I think it's enough. I don't prepare for much more contents. If the effect is good, I will continue this seminar next week. Okay, that's all.